What happens if you build a microscopic guillotine and just violently chop a single uncuttable particle of light in half?
Well, you definitely don't get two smaller pieces, that's for sure.
Right, you get infinity. Welcome to the deep dive, where our primary mission today is to completely shatter your understanding of empty space.
And, the fundamental building blocks of reality itself.
Yeah, exactly. Because, it's a premise that sounds like it belongs in a sci-fi movie,
Hmm.
but it's actually grounded in some of the most rigorous, mind-bending physics going on right now.
It really is. And when we think about the physical world, we instinctively rely on this idea of fundamental building blocks,
Like
right?
with Lego set.
Exactly. Like Legos, you can smash a giant Lego castle into 1,000 pieces, but eventually you get down to that single tiny one-by-one brick.
Or the piece you just cannot break down any further no matter what you do.
Yeah. By definition, an elementary particle, like a photon, a single particle of light, it cannot be broken into smaller pieces. It's the absolute bottom floor of reality.
And we find that comforting, I think. You and I, we like knowing there's a limit to how far things can be divided. It gives the universe a sort of reliable structure.
Oh, absolutely. But today, we're going to look at what happens when you just decide to ignore the rules and take a quantum saw to the universe's smallest, most unbreakable Lego brick anyway.
I love it. So for everyone listening, we're pulling these insights from a really fascinating June 2026 article in phys.org.
Right. Written by Sam Jarman.
Yes, Sam Jarman. And it covers a theoretical study published in Physical Review Letters by Johannes Skar and his colleagues. Though, I have to admit, our source stack today also hilariously includes a Cloudflare security verification page.
Oh, yeah. The modern reality of scientific research right there.
It's ridiculous. Sometimes the hardest part of exploring the quantum realm is literally just getting through the front door of the journal.
I mean, you're just trying to get the raw equations, right?
Yeah. I was trying to dig into the primary journal link on apps.org to pull the math for us, and I get hit with a bot check. Please wait while we verify you are not a bot.
The irony is just, it's so good.
Right. Here we are, trying to uncover the deepest secrets of the quantum universe. And I'm sitting there having to prove to a computer that I know what a crosswalk looks like.
It definitely adds a certain flavor to high-level physics. You're trying to peer into the fabric of space and time. But first, please identify all the images containing a traffic light.
Exactly. But, once we got past the digital bouncer, the research from Scar's team was entirely worth the detour.
It really was.
Okay, let's unpack this. To understand how you can possibly get an infinite swarm of particles out of one single indivisible thing, we first need to look at the thought experiment itself.
Right, the incredibly precise setup these researchers designed to attempt the impossible.
Because to even attempt this cut, we have to look at the dual nature of a photon. The text makes it really clear a photon isn't just a tiny, hard little sphere flying through space.
No, not at all. Like any quantum particle, it exists simultaneously as a single localized particle and an extended wave.
A wave that's literally spread out across space.
Exactly. And that dual nature, that is the mechanism that makes this whole theoretical experiment possible.
So how does that actually work in the context of the field?
Well, in quantum field theory, a photon is essentially an excitation, like a ripple in the electromagnetic field.
Okay.
So when we say it's an extended wave, we mean that this ripple isn't just happening at one infinitely small mathematical point.
It has an actual size.
Right. The wave packet actually has a physical length as it travels through space. And Scar's team realized that if you treat the photon as this extended electromagnetic pulse traveling through space, well, you might be able to intercept it mid-flight.
And that's where they introduced this optical shutter, right?
Yes. They designed a thought experiment involving an optical shutter.
The source basically describes this thing as a very, very fast mirror.
Imagine a mirror that can just be switched on and off with unimaginable speed.
Like faster than we can even really visualize.
Oh, absolutely. So the idea was to send a single photon towards this shutter and switch the shutter on right in the dead center of the photon's pulse.
So the mirror acts as a physical block.
Exactly. If it transitions fast enough, it intercepts the photon mid-pulse, effectively snipping off part of this extended wave.
Okay, let me try an analogy to ground this for you listening. Imagine you are in a massive swimming pool, and you create one single perfect wave rolling across the water.
Okay, I like this.
So that wave is our photon. Now imagine dropping a massive steel blast door directly into the water right in the middle of the pool, exactly as the waves is passing through.
Right, just slamming it down.
Yeah, you're slamming a wall right through the middle of the wave's physical spread.
That is actually a highly accurate visual. You are violently interrupting the spatial extension of that wave mid-transit by introducing a sudden boundary.
Okay, but let me challenge that framing for a second on behalf of anyone listening who remembers their basic high school physics.
Sure, go ahead.
If a photon is an elementary particle, meaning it cannot be divided by definition, it has no subcomponents, how can the math of quantum equations even allow a mirror to snip it?
That's the big question.
Right. Aren't we just breaking the fundamental laws of physics right out of the gate here? How does the mathematical model even process a scenario that is supposed to be physically impossible?
Well, that is the core mathematical hurdle the researchers had to overcome. Scar's team had to rely on the advanced equations of quantum field theory to track what happens to the underlying electromagnetic field itself.
So they aren't looking at the photon as an object.
Exactly. You aren't slicing a hard physical object like you'd slice an apple with a knife. You are introducing a new boundary condition, the mirror, into the electromagnetic field that the photon represents.
Ah, okay. That makes sense.
Yeah, quantum equations are perfectly capable of calculating how a wave function transforms when a sudden physical boundary is introduced into its path.
So the laws of physics don't break.
No, they just follow the new geometry of the field to its natural mathematical conclusion.
Wow. Okay, so here's where it gets really interesting. Because the equations churn through the sudden interruption of the optical shutter, and they output a result that literally no one would intuitively expect.
It's completely wild.
When you drop that blast door on the quantum wave, the shutter does not produce half a photon on one side and a vacuum on the other.
Yup.
And it doesn't just destroy the photon either. Instead, the shutter conjures a complex quantum superposition containing infinitely many photons simultaneously.
Infinitely many photons, suddenly existing all at once, just generated from the attempt to cut just one.
I mean, it sounds like absolute physics magic. You start with one, you introduce a fast boundary, and suddenly you have a swarm of infinity.
It really does sound like magic, yeah.
But to understand why this happens, we have to radically shift how we view empty space, right? The text highlights this vital concept in quantum mechanics. Empty space isn't truly empty.
Right. It is not a void. We have to completely discard the idea of a vacuum as a blank canvas.
Well, it's not just nothingness.
Exactly. In quantum field theory, what we call a vacuum actually seethes with fluctuations in the electromagnetic field.
Even when there's nothing there.
Even when there are no permanent particles present, the underlying fields are constantly bubbling with energy. Temporary particles are constantly popping into and out of existence.
And just to prove to you listening that this isn't some weird mathematical quirk, but a proven physical reality, we can look at the Casimir effect.
Oh, perfect example.
Yeah, if you take two completely uncharged metal plates and place them incredibly close together in a perfect vacuum, the vacuum fluctuations, these temporary bubbling particles, they actually exert a measurable physical pressure that pushes the plates together.
Which is mind-blowing.
It is. The empty space inside the room you're sitting in right now is actually a perfectly balanced boiling pot of unseen electromagnetic energy.
And what's fascinating here is how the introduction of that incredibly fast mirror interacts with that boiling pot.
The blast door in the pool.
Right. By rapidly switching the optical shutter to try and cut the single photon, the team found that the sheer speed and violence of that new boundary actually disturbs these underlying vacuum fluctuations.
It agitates the field.
Exactly. The sudden change in the electromagnetic boundary conditions agitates the vacuum. And when you agitate a quantum field that violently, you impart energy into it.
And that energy has to go somewhere.
It causes those seething virtual fluctuations to snap into permanent reality.
Yeah.
It spontaneously creates new photons out of thin air.
Okay, let me push back here to make sure I'm grasping the exact mechanics of this.
Sure.
If we are actually cutting the original photon, but rather, waking up the vacuum around it with this fast mirror, does the original photon still exist in its original state? Or is it consumed by this new infinite swarm?
That's a great distinction. The original photon state becomes inextricably entangled with the newly agitated vacuum.
Entangled, okay.
Yeah, the math shows a superposition, which means multiple potential realities existing simultaneously. The original state of the single photon and the highly excited, infinitely populated vacuum state are blended together.
So the fast mirror essentially acts as a pump.
Yes, transferring energy into the field and triggering a localized quantum avalanche.
An infinite quantum avalanche. I mean,
Yeah.
that's just, it's incredible. But that leads us directly into what has to be the most glaring problem with this whole theory.
I think I know where you're going with this.
If we are summoning infinite photons into existence simply because we swung a fast mirror through a vacuum, why wouldn't we instantly see a blinding, universe-ending flash of light?
Right, where is the light?
Exactly. If the math says there is an infinite swarm of light particles, where are they?
And that brings us to what is undoubtedly the most counterintuitive, deceptive detail from the entire study. It involves the stark difference between what is happening globally, across the whole quantum system, versus what you observe locally.
Yeah, the text notes that if you were to look only at the region immediately on either side of where the shutter operated, just a tiny localized snapshot right next to the mirror, the state appears deceptively normal.
Deceptively normal is the perfect phrase, because if you set up a standard photon detector right next to the shutter, it would simply click once.
Just once.
Yep. It would register a single photon on one side and empty vacuum on the other.
So depending on where I look, reality is completely different.
Essentially, yes.
Locally, right up close, it's just one normal photon and some empty space. But globally, mathematically, it's an infinite, complex swarm. How can both of those things be true at the exact same time without breaking logic entirely?
Well, this raises an important question, doesn't it? It challenges our fundamental understanding of how quantum systems are measured and exactly how information is localized in space.
Because in classical physics, things are pretty straightforward.
Right. If there's a thunderstorm covering an entire city, looking only at your front porch still means you are inside a thunderstorm. The global reality applies to the local reality.
The thunderstorm doesn't disappear just because I'm only looking at my driveway.
Exactly. But in quantum mechanics, the infinite swarm isn't a collection of separate, hard little marbles bouncing around the room.
It's not physical objects in that sense.
No, it is a distributed property of the entire field. The infinity is encoded in the complex correlations and entanglement across the whole extended wave, across the entire global system.
It's almost like, imagine a massive, impossibly complex symphony being played by a million instruments.
Okay, I see where you're going.
But if you walk up and listen through a tiny soundproof keyhole, the acoustics are so weirdly filtered that all you hear is a single person playing the triangle.
That is a brilliant way to put it.
Wow.
To translate that acoustics analogy back to the actual quantum field theory, it is all about collapsing the wave function.
The observer effect.
Right. The infinite swarm is held together by delicate quantum entanglement across the entire spatial wave. When you make a purely local measurement, when you listen through that tiny keyhole, you force a physical interaction that severs those broad global correlations.
So just by measuring it locally, you destroy the global swarm.
By demanding a local answer, you cause the complex wave function to collapse. The system discards the infinite complexity and drops down to its simplest, lowest energy localized projection.
Which is just a single photon.
Exactly.
It hides in plain sight. An infinite swarm hiding behind the mask of a single normal particle, because the very act of trying to observe it closely forces it to put the mask back on.
Beautifully said.
So what does this all mean? Why should you, as the listener, care about a highly theoretical math problem involving imaginary fast mirrors and quantum fields?
Well, because it forces us to confront the true nature of reality. It offers a striking illustration of how quantum particles completely defy the rules of everyday objects we interact with.
We're so conditioned to think of the universe as a collection of separate, divisible things moving through empty dead space.
And this research proves that classical view is just an illusion.
And Scar and his team, they're planning to push the math even further, right?
Yes, they are. They want to explore whether the same bizarre physics applies when more than one photon is involved. Like what happens when you drop the optical shutter on an entangled pair of photons?
That's going to be messy math.
Very messy. But even more fundamentally, they plan to extend this analysis to other elementary particles such as electrons.
Which changes everything because photons are massless.
Exactly. Photons are massless particles of light. Electrons have mass. This is where the implications for quantum field theory become truly staggering.
So if you build a quantum guillotine for an electron,
And the math holds up, do you get a localized superposition of an infinite swarm of massive particles?
oh, wow.
Yeah. The questions regarding energy conservation and field dynamics in that scenario are pushing the very edges of modern physics.
It feels like they found a tiny crack in the facade of classical reality, and now they're just using complex field equations to pry it wide open to see what's hiding underneath.
That's exactly what they're doing. And if we connect this to the bigger picture, it synthesizes a profound realization about the environment you inhabit.
The empty space.
Right. The empty space you walk through every single day, the space between your eyes and the screen, the space in the room around you, it is not a void. It is a highly sensitive, seething web of potential, just waiting to be disturbed.
It's alive with quantum fluctuations.
Alive is a great word for it.
And it only takes a sudden enough boundary, a fast enough physical interruption, to pull that massive potential out of the underlying math and into physical reality.
The fabric of the universe is far more interconnected and far more reactive than our human senses or our everyday experiences could ever perceive.
Man, let's just recap what we've unpacked on this deep dive because it is heavy.
It is a lot to take in.
We started with the idea of a fundamental, unbreakable Lego brick, a single photon of light. We learned that if you design a microscopic, lightning-fast optical shutter to try and cut that uncuttable wave in half, you do not get two pieces.
No, you definitely don't.
Instead, the sudden, violent boundary agitates the seething, boiling quantum fluctuations of empty space itself.
And in doing so, it conjures a quantum superposition containing infinitely many photons.
An infinite swarm of light that, bizarrely, remains completely hidden from local observation.
Right, because the act of measuring it severs its global entanglement, forcing it to masquerade as a deceptively normal single particle.
It's the ultimate magic trick performed by the universe itself, backed up by rigorous mathematics.
Truly.
But before we sign off, I want to leave you with one final thought to mull over as you go about your day. We've established from the source text that simply disturbing the empty electromagnetic field with a fast-moving boundary creates a superposition of infinite particles.
Right. The math demonstrates that the speed and suddenness of the boundary are what trigger the vacuum.
So take a look around. Our universe is not static. It is utterly filled with violently moving objects, chaotic forces, exploding stars, collapsing black holes, and rapidly shifting electromagnetic fields.
Constant motion, constant boundary.
Exactly. If a theoretical mirror in a lab can summon an infinite quantum swarm just by switching on and off fast enough, how many invisible infinite quantum swarms are being spontaneously generated in the empty spaces all around you right now, completely undetected, hiding right behind the deceptive illusion of normal space?
Well, it definitely changes how you view the empty air in the room.
It really does. Next time you think you're alone in an empty room, just remember the seething vacuum. Thank you so much for joining us on this deep dive. Keep questioning the world around you, keep looking past the illusion of the everyday, and we will see you next time.